Okay, I think we can get started. So, good morning, everyone. Welcome to the GIST Sea Level Rise seminar. And we're very glad to have Dr. Kyle Mattingly with us. He is a research scientist in the Space Science and Engineering Center at the University of Madison, Wisconsin-Madison. And his research investigates the complex interactions among Earth system components that determine the course of polar climate change, with a particular focus on how extreme atmospheric events affect the Greenland ice sheet. And he uses a variety of observational modeling and remote sensing data sources and techniques for this work. Dr. Mattingly is involved in the polar radiant energy in the far infrared experiment PREFIRE mission, and he is helping to develop algorithms for matching auxiliary meteorological and satellite data to the PREFIRE spacecraft orbit. Prior to his current position, Dr. Mattingly was a postdoctoral associate in the Institute of Earth, Ocean, and Atmospheric Sciences at Rutgers University, and he earned his BS in meteorology from Western Kentucky University and his MS and PhD from the University of Georgia. And today he will be speaking on the topic exploring the historical and future impacts of polar atmospheric rivers. So, welcome, Kyle.
Thanks, Patrick. I guess I should share my screen here. Let's see. Okay, can you see that now?
Yes,
Okay,
yes, but not the full screen.
okay, let me see if I can. Okay, how about that?
Yes.
Okay, great. All right, well, thanks a lot, Patrick, for the invitation, and thanks to all of you for, thanks to all of you for joining this morning. Like Patrick said, my name is Kyle Mattingly, and I'm a research scientist in the Space Science and Engineering Center at the University of Wisconsin, and going to be talking about polar atmospheric rivers today. Um, and yeah, first off, I'd like to just kind of preface this talk by saying this is an area of research that is something I'm deeply interested in and have done work on in the past. I've maybe strayed a little bit away from publishing on this in the past few years, but I'm still actively engaged in the community. So with that said, I kind of wanted to make this talk maybe a little more of like a literature review with my own work mixed in than you maybe would see from some of these other kind of talks, and just try to like put in context what we've learned about polar atmospheric rivers and what the outstanding questions are still. Um, so yeah, I hope you'll just keep that in mind as I go through this talk, that this is my work mixed in with interesting results from others and trying to put that in context. And of course, giving credit for other people's work wherever, trying to make it clear what's my work and what's other people's work. Um, so yeah, so this background on the title slide is something that I think kind of encapsulates polar atmospheric rivers pretty well. This is an event in August 2021, a Greenland atmospheric river event that was responsible for melting, reaching up to the highest elevations of the Greenland ice sheet for what's happened only a few times in the past century or so. And what I think is neat about this image is you can kind of see the clouds and the ice sheet surface kind of peeking through. This is kind of like a medium zoomed in area of Western Greenland. And it kind of captures the atmospheric and the surface components of polar atmospheric rivers pretty well, I think, because you have these clouds that are probably enhancing downwelling long wave radiation and kind of trapping some heat near the surface. And then you can also see these melt ponds, or meltwater lakes, I should say, on the ice sheet surface during this event. Okay, so yeah, just kind of going through the structure of the talk here. What I'd like to do is kind of start off with kind of a zoomed out background of what atmospheric rivers are, um, and then go into how the concept of atmospheric rivers kind of made its way into polar research in the last, I would say, decade or so. Um, and then kind of go through atmospheric river impacts in the two polar regions. So starting off with Arctic atmospheric rivers, which is kind of more of my zone of research, and then also reviewing some of the research on Antarctic atmospheric rivers and kind of some of the similarities and differences between the two poles. And then get a little bit into atmospheric river trends and future projections. And then also just talk a little bit about some of my and others' planned future research in this area of polar atmospheric rivers. Um, this is another kind of satellite image that I think is cool. This is the July 2012 atmospheric river event. And you can see this. I'm not sure if you can see my mouse or not, but you can see this cloud plume associated with a very strong atmospheric river that was associated with very extensive Greenland melt coming up from the south. Okay, so starting with the first section, the background of atmospheric rivers. Yeah, so I'm sure most people have probably heard this term. It's kind of become in vogue in the literature and in the public in recent years, but just as a primer, in case you aren't quite aware of what this term means, basically, the term atmospheric river refers to a long and narrow corridor of moisture transport in the atmosphere. They're typically looked at as mid-latitude and high-latitude events, and they typically are associated with other dynamical synoptic features that have been studied throughout the history of meteorology, such as extratropical cyclones and low-level jets and warm conveyor belts. There's a lot of overlap and sometimes some debate between those different terms, but I would say the atmospheric river mainly refers to the moisture transport component of those atmospheric dynamics. Um, and part of what makes them so notable and such a important topic to study, I think, is how they're so disproportionate in terms of how much moisture they carry compared to their area. So at any one time, there's roughly 10% of the mid-latitude and polar latitudes covered by an atmospheric river in area, but around 80 to 90%, depending on which study you look at, of the polar moisture transport throughout the world in the mid-latitudes occurs through these very narrow events. So there's kind of something about the mid-latitude atmosphere and it getting into the high latitudes that kind of tends to organize itself into these narrow plumes of moisture transport that then can have very big impacts whenever they affect certain regions. So just a quick background on where the term atmospheric river came from and some of its history. Like I said, these are features that are linked with other atmospheric dynamics that have been studied for a long time, getting all the way back into the 1930s, where the first studies of what Rossby called moist tongues, looking at isentropic charts. That's what you see on the top here. We're kind of the precursor to what we call in the modern day atmospheric rivers. And Wei-Ming Mo has a really nice paper from 2022 that kind of resurrects this early history of when people first started looking at these moist filaments in the atmosphere. And then throughout kind of the middle of the 20th century, other people's kind of started added different terms to distinguish different aspects of these atmospheric features. So the term low-level jets got introduced, and also the warm conveyor belts, which refers to kind of overlapping but not exactly the same features as atmospheric rivers. So then in the 1990s, that's where studies came along that first started calling these things atmospheric rivers, which originally this term was coined because they can carry as much moisture as the Amazon River discharges kind of instantaneously. So it was kind of an analogy to kind of liken these very narrow features in the atmosphere to terrestrial rivers. And it also fit because in terms of the amount of water vapor that they carry, they're kind of comparable in total mass to terrestrial rivers as well. And then from kind of around the mid 2000s to now is when this term really kind of took off in research circles, but also in the public domain, I would say. So, now you hear, even among like news reports or, the general public, people are kind of aware of the term atmospheric river now. And sometimes they might have different opinions on it, but now people have really become aware of this term, and it's kind of really taken off in research. So that's what this graph is showing here, is if looking at the Google Scholar hits for atmospheric river over time, and how really since kind of the mid 2000s, and especially I would say even the past 5 to 10 years, the growth on research in this topic has really taken off. Okay, so um, part of why we care about, or most of why we care, I would say, about atmospheric rivers is the impacts they have whenever they, come from a certain region, such as the lower latitudes, and then we often call it making landfall in mid-latitude areas, or just come to be in mid-latitude areas. And whenever they do make landfall, they contribute a large amounts of the annual precipitation, especially in certain favored regions of the globe, like the western coast of continents, or especially where there's a mountain range and some topography to force that moisture up whenever it reaches the continent. Um, and I think one of the key things to point out that's really been made clear about just the past several years of atmospheric river research is kind of like the dual nature of atmospheric river impacts. So if you take a place like California, where atmospheric rivers are very impactful, um, they're kind of a extremely critical and necessary part of the hydroclimate, because so much of the annual rainfall comes from just a few atmospheric river events, especially more towards the southern part of California. So they're beneficial in that way, and kind of a must-have for water resources. But then when they get too strong, or they last too long, or that there's too many in a short amount of time, then they become very hazardous, and they can cause flooding and landslides and all kinds of negative impacts. So that's what this atmospheric river scale on the right here was kind of designed to quantify, was um, to kind of try to give the public a kind of a hurricane-like scale, or kind of Saffir-Simpson-like scale to be aware of atmospheric river impacts, and kind of categorize them according to either mostly beneficial or mostly hazardous impacts. And part of the reason why I included this background is I think there's kind of a good analogy with polar atmospheric river impacts, where polar atmospheric rivers often either add mass to the ice sheets, or whenever they become too strong and too warm, they can very quickly cause very strong ice sheet melt. So I'll kind of get into that some more later. And then I just wanted to, since this is something that's happened very recently, and as Patrick said, Western Kentucky University was my alma mater, so thought I would throw this in here about a very recent atmospheric river impact that's going on. So yeah, this is last week, and you can see we have this very strong moisture plume coming up from the Gulf into the Ohio Valley, where you had very extreme rainfall amounts, up to around like 15 or 15 plus inches in Kentucky, and other parts of Arkansas and Tennessee, and the Ohio and Mississippi River valleys. So yeah, this is an example of an atmospheric river that was mostly on the hazardous side, unfortunately. Okay, another aspect of atmospheric river science I'd like to point out from just a global perspective, is that there have been all kinds of different detection tools that have been developed to detect these events and build databases. So the very first atmospheric river detection algorithm was developed by Zhu and Newell in 1998, and since then there's been quite a few, probably in the, I don't know, somewhere in the range of like 50 in the literature of different atmospheric river detection tools that have been used to pick up on these events. And I think it kind of started because there was, different people and different researchers in different regions were interested in atmospheric river impacts. So you had algorithms that were developed to try to pick up atmospheric rivers in California, or the coast of Chile, or the polar regions, and those all kind of dispersed into different detection algorithms. And then in the past 10 years or so, there's been this effort that Christine Shields has done a really good job of leading, of trying to kind of corral all those different detection tools and figure out where they agree and disagree and where they're useful, and, and maybe most critically, how you can use them for future climate projections to tell us about how atmospheric rivers are going to change in the future. Um, and that's something I'll get into a little more later for on the polar side of things. I think probably the key points that I think these papers from the ARTMET project emphasize um, is that the choice of atmospheric river detection tool that you make is highly significant on the qualitative results that you get from your study. Um, so, for example, this O'Brien et al. 2021 paper was looking at future projections of how atmospheric rivers are going to change in future climate states. And they found that which AR detection tool that you choose has a much larger impact on the results that you take away compared to like the mission scenario or the climate model that you use for your future projections. So there's been a big effort in the community to compare these different tools and try to provide context and recommendations for other researchers about how to use them. That's been going on. Okay, so with kind of the global atmospheric river context out of the way, I'd like to dive more into the how this concept kind of got applied to the polar regions. Um, so I'd like to start off with some of the important papers that were first published on atmospheric rivers in the polar regions and how I think they more or less set the stage for how this field was going to develop up until the present, very early on. Um, so this is showing this plot is showing a figure from William Neff's and co-authors 2014 paper looking at the July 2012 atmospheric river that affected Greenland, and showing how this really strong atmospheric river was a key part of this melt event that was pretty much unprecedented in the satellite record, at least over Greenland. Um, and there was another paper in 2015 that kind of went into more detail about what the moisture sources were for this atmospheric river event and how it's really brought this very exceptional lower latitude moisture plume up to the polar regions. So this was what really kind of inspired me whenever I was starting to do my PhD, start my PhD around this time and think about atmospheric river impacts. And I think this July 2012 event has really shaped the field of atmospheric rivers in Greenland, at least. Um, and then for on the Antarctic side, I think the one of the earliest papers that I'm aware of anyway is Irina Koronitskaya and co-authors paper in 2014 that was kind of looking at a very opposite impact of atmospheric rivers. So they were looking at Princess Elizabeth Station in East Antarctica, and they showed that just a very small amount of very strong atmospheric rivers were basically responsible for nearly all the snow accumulation over this 2009 to 2012 time period. And particularly in 2009 and 2011 was when these atmospheric rivers occurred. And then you could see in 2010 and 2012 when you didn't have these just very short-lived but very strong moisture transport events, there was hardly any snow height added to the ice sheet at this station. So yeah, so I think these were two very important studies for setting the stage for atmospheric river impacts on the polar ice sheets. And then a little bit different perspective, there's kind of this other branch of the literature that developed that was looking at what they called Arctic moisture intrusions or Arctic warm intrusions. That was more focused on Arctic sea ice and what was happening over the ocean basin of the Arctic Ocean. So I think this is kind of a unique thing for the Arctic relative to the Antarctic because, obviously in the Antarctic, you don't have this open ocean basin, so you don't have these type of events to study like you do in the Arctic. So that's kind of, I guess, my hypothesis for why this literature kind of developed on its own, and then kind of in recent years has been brought together a little more with the Greenland atmospheric river research. Um, yeah, a lot of these early studies were focused on wintertime warming events in the Arctic and how these moisture intrusions from lower latitudes really warmed the surface and in some cases either slowed the sea ice growth or even maybe caused a little bit of cold season melt of the sea ice or declining of the sea ice uh, through particularly through downwelling long wave radiation that's brought by the enhanced cloud cover and the enhanced water vapor in the atmosphere during these events. And there some of the key takeaways, I think, from this research on these Arctic moisture intrusions is that they tend to come through preferred pathways into the Arctic. So that's what this figure on the top from Woods et al. 2013 is showing, is that the Atlantic sector of the Arctic is a very important gateway for these events, and maybe to a lesser extent also the Pacific sector. And then another, I think, important study on these Arctic moisture intrusion events was this Liu and Barnes 2015 paper, which showed that not only are there preferred pathways for moisture transport going into the Arctic, but also that these very extreme events, these very strong instances of exceptional moisture transport actually account for a majority of the moisture transport total, or I would say a majority if you look at the color bar, but in some cases, a plurality, a very disproportionate amount of the moisture transport coming into the Arctic, especially during the cold season. So I think this is kind of moving towards a little bit the atmospheric river concept applied to these moisture intrusions because it's looking at, again, very short-lived extreme events that account for a large proportion of the total moisture transport. Okay, so like I said, I think these studies back in the mid 2010s that were the first to kind of apply the atmospheric river concept to the polar regions. Um, I think they by and large, from my perspective anyway, they really shaped how the field would develop over the next decade or so. So already you can see for example, from the Neff et al. 2014 paper that they were looking at ice sheet melt as a primary impact of polar atmospheric rivers. And then the Gorodetskaya et al. 2014 paper was looking at accumulation and positive contributions to surface mass balance as a primary impact of polar atmospheric rivers. And I think that's kind of been the focus kind of from there on out when it comes to ice sheets is, there's been a lot of papers looking into the details of how that happens and, putting more context into play. But I think that basic balance between the melting and accumulation impacts of ARs on the ice sheets has kind of stayed very constant in the literature. And then some of these other second order effects that I'll get into a little bit later on started kind of come into play too, that people started looking at how ARs affected other components of the ice sheet mass balance and how they interacted with the topography of the ice sheets. But I think in all of this, probably the key question whenever people are studying polar atmospheric rivers is what is their overall influence on sea level rise? And why I think this is an appropriate topic for this seminar series is that I think polar ARs will have an influence both historically and in the future on the ultimate trajectory of sea level rise from the polar ice sheets. And then, yeah, these early studies also set the stage for impacts on Arctic sea ice, and that's kind of been extended to the Antarctic in recent years as well. And yeah, some of these other impacts on Antarctic ice shelves and on the atmospheric dynamics I'll get into a little more later too. Okay, so that's kind of the Arctic and Antarctic introduction, and then I'll dive a little bit more into Arctic atmospheric rivers, which is a little bit more of my wheelhouse, I would say. So starting with the impacts on the Greenland ice sheet, and specifically the surface mass balance. This is a figure from Mattingly et al. 2018 that's showing how atmospheric rivers events compared to non-atmospheric river times in terms of how they affect the Greenland ice sheet surface mass balance, at least from a regional climate model simulation of the surface mass balance. And you can see on the top left that during the summer, atmospheric rivers, especially the strong ones, which is what I focused on more in this paper, kind of again have this dual impact. Even the strongest atmospheric rivers during the summer tend to add some mass in the higher elevations of the ice sheet. So even though they might be causing melts, up to, in some cases, fairly substantial elevations on the ice sheet, most of these events are still causing accumulation, up in the percolation zone and the accumulation zone of the Greenland ice sheet. But then at the same time, they also tend to cause pretty strong melting in the lower elevations of the ablation zone of the ice sheet. But then when you get into the non-summer events during the cold season, those events are almost exclusively going to add mass in the form of accumulation to the ice sheet. And for the strongest events, there might still be some melt around the margins during the cold season. But by and large, that's going to be outweighed for the most part by accumulation. So it's really, I would say, the summer strong atmospheric river events that you kind of have to watch for the strongest melting and runoff impacts in Greenland. And I think I didn't put the figure in here, but one key takeaway is also that these very strongest summer atmospheric rivers, these extreme events, such as the July 2012 atmospheric river or the August 2021 atmospheric river that's shown here, kind of the ceiling on how much melt and runoff they can cause is higher than how much typically the strongest atmospheric rivers in the cold season add to the ice sheet through accumulation. So, yeah, it's kind of a little complicated to talk through sometimes, but the very strongest atmospheric rivers during the summer have the potential to cause a lot of melts, and then atmospheric rivers are beneficial through a lot of other times of the year in that they can cause enhanced accumulation and increase the surface mass balance, but that tends to be a little more muted and of an effect than the very exceptional pulses of melt that happen during the strongest summer ARs. And that's kind of typified by some of these very strong atmospheric rivers in the past decade and a half or so that have brought melt to the very highest elevations of the Greenland ice sheet, including Summit Station, which is very rare, but has happened more often just in the past couple of decades. And most of these events have occurred in association with atmospheric rivers. Lost the light in my room here, but just gonna soldier on. And then, yeah, so one of the other aspects that I think is interesting about atmospheric rivers in Greenland and Antarctica is how strongly they interact with the ice sheet topography. So this is what some of my research in recent years has shown, is that whenever you have an atmospheric river making landfall on kind of the upslope side of the ice sheet, it tends to, that upsloping forces the air up and forces clouds and precipitation to form. But you also still often get melt during the strongest ARs in this kind of cloudy sky regime where you're downwelling long wave radiation and your sensible heat flux is enhanced on the windward slope. But then at the same time, or often kind of a day or two later on the leeward slope, as that airstream flows down the topography of the ice sheet, it can also warm the atmosphere through a very different mechanism, which is the Foehn effect, or the downsloping that causes clearing and sinking air, but also that air is also warmer than normal, and it can cause melt through that kind of clear sky atmospheric regime. And so that's what these two figures are kind of showing, is if you this is an example of it from 2014, where an atmospheric river is making landfall on the west coast of Greenland, then it flows up and over the ice sheet, and then over the northeast part of Greenland, you have foam that's detected in the green here, and also this is the melt simulated by the Rightmo model in the warmer colors as the air is flowing down, and that's kind of shown in cross-section view in a composite sense from this figure on the right, showing that, especially if you focus on the bottom, which is the 90th percentile atmospheric river events coming through this cross-section. Yeah, you get this upslope flow along the western side of the ice sheet. And the pink contours show where the air is rising, or you have negative vertical, or yeah, negative omega, so positive vertical velocity. And then as that air flows over the ice sheet and down, you get these very well-defined black contours where the air is flowing down the slope and is being kind of pulled down from a little bit further up in the troposphere. And you get clearing and drying and melts on the lee slope from that regime as well. And this is kind of shown nicely by Lily Hahn et al.'s paper in 2020, where they showed that in order to reproduce the trends that have been observed in Greenland cloud cover that have kind of contributed to the enhanced Greenland melt in recent years, and also to explain the total amount of melt that was observed in the July 2012 event, you need to include the ice sheet topography in your model. So something about that dome topography of the ice sheets really has a strong impact on the kind of melt regimes and the total melt that you get on the ice sheet. Okay, on the flip side, looking at the mass gains of the Greenland ice sheet related to moisture transport, Claire Pedersen et al.'s paper in 2022 showed that there are kind of distinct moisture transport regimes that lead to snow accumulation at Summit Station, where you sometimes, especially during the summer, you get moist air flowing up the western slope of Greenland, and that causes enhanced snowfall at Summit Station. And these are kind of, again, like the not the strongest, most extreme atmospheric rivers, so they're mostly going to cause accumulation at the higher elevations. And then during the autumn, you get kind of this Icelandic low regime that favors snow accumulation at Summit Station, where air is kind of flowing, moist air is flowing up from the southeast part of Greenland. And yeah, I put a little figure on here. This is just, again, a recent event that I was able to find from this past March. It's probably not the most extreme event out there in the record, but it was just something from recently that shows how you have this kind of southeasterly moisture transport coming into Greenland, and at the same time, that's causing kind of a spike in the daily surface mass balance added to the ice sheet. And I'll also put a plug for Alana Wedham's paper that's hopefully will be coming out soon, that shows that it's very uncommon for these atmospheric rivers to actually reach the Summit Station itself intact. There's only, I think it was maybe like 1% of time steps when they do, but they disproportionately contribute to the total snowfall at the top of the Greenland ice sheet whenever they do actually make it up there. I think it was somewhere still pretty low, but like 5 to 6% of the snowfall at this highest elevation was related to ARs. Okay. And then another interesting impact, again, this is not my work. This is Jason Box's paper from 2023 co-authors, but it's showing how atmospheric rivers also can cause very exceptional rainfall over the Greenland ice sheets, and how this reanalysis has shown an increase in the total rainfall and proportion of rainfall happening in Greenland. And this is again this August 2021 atmospheric river, where they showed that it was the highest, I think, total rainfall that they could find in this reanalysis record from 1990 to the present. And again, it was associated with this very strong atmospheric river. So yeah, rainfall is typically a pretty small component of the mass balance in Greenland, but these atmospheric rivers can cause some pretty exceptional rainfall events to happen as well too. And okay, just quickly, some of the other second order effects that I'm calling them that atmospheric rivers can cause. So I guess what I would call the primary effects are the effects on surface mass balance, where atmospheric rivers either directly cause more melting or directly cause more accumulation, and that's directly just goes, straight into the positive or negative surface mass balance. But they can also kind of have these more indirect effects, such as like whenever you get an atmospheric river or a moist airstream coming up into the polar regions, that can contribute to the development of a high pressure blocking system that can then go on to cause warming in Greenland, even though the atmospheric river itself may not have, directly made landfall in Greenland. Um, they've also been implicated in speed up events of outlet glaciers. So times when these outlet glaciers speed up on very short timescales have been linked to some atmospheric river events. And then also, especially the July 2012 melt event, which was again really exceptional, that can cause long-term impacts in terms of changes in the firn structure. So some of these papers have shown that you can still see this ice layer from the July 2012 melt event that's still present in the firn below the surface and is still affecting the firn retention capacity of the ice sheet. So yeah, even though these events can maybe last for a day or two, their effects can linger for like a decade or more if they're strong enough. Okay, I think I'm gonna try to go a little more quickly through this because we're running a little short on time, but yeah, again, some of the other impacts of atmospheric rivers in the Arctic are they can cause these warming events during the winter, which a lot of studies have shown in the past. Sometimes they call them atmospheric rivers, sometimes they don't. And this is another recent example I pulled out where, yeah, especially this early February spike that you can see on one of Zach Laib's plots in the Arctic temperature. And you can also see how the Arctic sea ice extent actually declined during the winter a little bit in early February this year. And again, this happened at the same time as this very strong atmospheric river or moisture intrusion came up into the Arctic in early February. Okay, so shifting gears a little bit to Antarctic atmospheric rivers, and I don't have nearly as much on this because this is something I've worked on kind of tangentially, but have not been as deeply involved in as some other members of the community. But I think it's still very important to talk about when you're talking about polar atmospheric rivers. Um, so yeah, the Antarctic atmospheric river research community, I would say, is very well developed and very collaborative at this point, which is really nice because they were able to come together and put out this really excellent review paper this year about what we know about Antarctic atmospheric rivers at this point. So that's what this figure is showing is Jonathan Willey was the lead author and um, really coalesced this community together. Um, so some of the, I guess, just things I'll point out about Antarctic atmospheric rivers and how they differ from the Arctic is they've really found through a lot of studies that the meridional component of IVT is really critical for capturing atmospheric rivers in Antarctica, which I think makes sense because of, again, just the configuration of the continents in the southern hemisphere and how, yeah, you really need a very strong meridional component to the moisture transport in order for it to be able to kind of get up over the topography on the coastline and make it into the Antarctic interior. Antarctica is also, I think, quite a bit different from Greenland in that in the interior of Antarctica, atmospheric rivers are almost exclusively a positive contribution to surface mass balance. So where in Greenland, you kind of get these mixed effects and it depends on the strength of the atmospheric river and the season and things. In the Antarctic, it's basically in the interior, ARs are almost exclusively beneficial in terms of adding surface mass balance. But where they can also cause negative impacts is along the margins, where they can cause surface melt on the ice shelves. And some studies have suggested that they can potentially contribute to weakening the ice shelves. They also affect Antarctic sea ice. I think this is kind of an area of research that's a little less far along than the Antarctic ice sheet research, but there have been some studies that have shown that Whenever you get atmospheric rivers getting into the sea ice zone in the southern hemisphere, they can cause sea ice declines and maybe sometimes kind of push the marginalized zone back through both dynamic processes, so moving the sea ice around, and also thermodynamic surface melt and warming. And again, some of Jonathan Willey's work has shown that atmospheric rivers may have also acted as weakening agents or triggers for some of these very well-known ice shelf collapses in the Antarctic Peninsula. Okay, to kind of wrap up on this topic, I wanted to talk a little bit about the atmospheric river trends, both in the historical record and the future. Um, this is going to be a short overview because I didn't quite get around to putting as much detail into this part as I would have liked. But I will say that there have been some studies that, including some of my work, has shown that in Greenland, these atmospheric river events have shown an increasing trend in the first part of the 21st century. And I think that's being borne out in some other studies too that have shown in other parts of the Arctic, especially the Atlantic gateway to the Arctic, these atmospheric river trends have been positive and increasing in recent years. The Antarctic Atmospheric River Review paper concluded that over much of the coastline in Antarctica, there actually hasn't been much of a detectable trend in the frequency of these events. But the exception to that is the Antarctic Peninsula, where that's kind of a little more exposed to the Southern Hemisphere storm track. And that has shown an increasing trend in atmospheric river frequency there. And getting into future projections, I think it's a pretty universal feature of future projections that in both polar regions, we do expect that there will be more moisture in the atmosphere, which will lead directly to more moisture transport from atmospheric rivers. I think it's fair to say, again, this is a topic that I wanted to dive a little more into before this presentation and didn't quite fully finish, but I think it's the literature, it's fair to say that the effect of increased moisture in the atmosphere kind of overwhelms any changes in atmospheric dynamics to contribute to these increases in atmospheric rivers. So I think most studies point to it being more of a Clausius-Clapeyron effect of increased moisture that will cause increasing atmospheric rivers. And I think this is another area where Greenland and Antarctica are quite distinct and where further study is needed, because in Greenland, I think it's pretty clear that if you have increasing atmospheric rivers and stronger atmospheric rivers, that's going to move melt higher up into the present day percolation zone and accumulation zone and cause more runoff. And maybe there'll probably still be some, accumulation during the cold season from more atmospheric rivers, but I think it's kind of more up in the air what the net effect is. Whereas in Antarctica, this projected increase in atmospheric rivers is actually expected to mitigate some of Antarctica's sea level rise potential from the dynamic losses from outlet glaciers, just because even in a warming climate, we expect most of the Antarctic ice sheet, at least for the next, I would say, century or so, I believe, in most scenarios, to still be cold enough to where this is mostly snow, and it's just more snow that's getting deposited by these atmospheric rivers. So that's, at least for the near-term future, might mitigate a little bit of Antarctica's sea level rise if we get more atmospheric rivers. Okay, so shifting gears to the last few slides I wanted to touch on. I just wanted to talk about some of my ongoing work and work with some colleagues that are addressing these topics of polar atmospheric rivers. So this is a slide on the PREFIRE mission that I'm a part of here. That's here at the University of Wisconsin-Madison and other institutions. So this is a mission that involves two CubeSats, both with a thermal infrared spectrometer, whose goal is to measure infrared radiation out to longer wavelengths than we ever have systematically from space before. So if you see these example spectra on the plot down here, anything from around anything past this kind of gap, past 15 microns in wavelength, is kind of our new observations that we're making with PREFIRE. And yeah, this is a really exciting project. We're just starting to release our data to the public. So if you want to click on that link or capture it, you can go check out some of our public data products. And I think this is this data will have some applications to polar ice sheet studies and polar sea ice and polar atmospheric rivers, because things that are happening with the surface emissivity of the ice sheets at these far infrared wavelengths, we're hoping to capture with PREFIRE. And it can also tell us things about the water vapor greenhouse effect throughout the full spectrum during these atmospheric river events, and potentially some things about cloud properties that the far infrared can kind of shed some unique light on during atmospheric rivers. Another project that I'm kind of just starting up is looking at how cold air masses form, especially in the northern hemisphere during the winter. And I think there is some overlap with polar atmospheric river research for this topic, especially in how the conceptual model for air mass transformation is kind of laid out in the literature, is that you get a warm air transport from lower latitudes that makes it into the Arctic and then cools through different radiative and turbulent processes. And then kind of, if nothing disturbs this air mass, then it'll continue to cool gradually and kind of become this Arctic air mass. But if heat is released back into the air mass, that can interrupt its formation and kind of reset the clock. And I think atmospheric rivers are potentially one perspective at looking at this process. So yeah, so I also want to look at some other satellite observations during these atmospheric river and cold air mass formation events, especially PREFIRE that I just mentioned, and potentially Earth care observations to look at the dynamics of cold air mass formation and how it relates to atmospheric rivers. Another project that we're excited about that's kind of just getting started up is an effort to extend these atmospheric river tracking algorithm comparisons to the polar regions. So this was kind of the brainchild of Joey Schnallbelt, who's a PhD student at Connecticut. And he kind of pitched to the atmospheric river tracking method group that we should have a paper that recommends how people should use atmospheric river catalogs in the polar regions. So that's an effort that we're just getting started up, and we're having some initial meetings and outlining a paper and stuff. But if anybody's interested in being a part of this work, it's a very kind of open community, and we're really hoping to kind of get a pretty large group together and just divide the work so we can really go after this year. So yeah, if you're interested in being a part of a project comparing polar atmospheric river detection tools, please feel free to get in touch. And the last little thing I'll make a plug for here is some of the maps that I showed in this presentation were from this quasi website that I have up. It's not much right now. I'd love to turn this into a real website in the future if I ever get time to. But yeah, if you ever get interested and want to look at what the GFS model or the European model is showing in terms of atmospheric rivers or IVT or surface temperature, precipitation, cloud cover, etc., over Greenland, I do have this little FTP site where you can go and check out some of these maps that get updated twice a day. And there's also a little, if you click on the HTML file in those folders, there's you can do a little draggable animation of the forecast maps. So yeah, this is very much a early effort kind of thing, but just thought I would throw in a plug here in case anybody's interested. Okay, so just wrapping up here. Yeah, reflecting a little bit on what we've learned from I think a decade or so of polar atmospheric river studies now. I think something that really sticks out is kind of this dual nature of atmospheric rivers in the polar regions, where they both can add mass to the ice sheets and take it away through melts. And I think that kind of mirrors the kind of global atmospheric river community's perspective, where they look at atmospheric rivers as having both beneficial and negative impacts. I think it's something that's become clear about both Greenland and Antarctica and Arctic sea ice for that matter, is that they're kind of these very extreme events that don't happen very often, but seem to be happening more often in recent years, but still maybe only every year or two or 5 years or whatever. But these very extreme events, I think, have qualitatively different impacts compared to other atmospheric rivers, like the July 2012 atmospheric river in Greenland, or the heat wave event in East Antarctica, which I believe was March 2022, is another example. And again, I think we've learned a lot about how the Greenland ice sheet and then Antarctica ice sheet are different in terms of how atmospheric rivers affect the surface mass balance, and how surface mass balance in Antarctica is mostly positive from ARs, and in Greenland it's a little more mixed and dependent on the event. And then looking ahead to the future, I think some of the key questions for this field are definitely what's going to happen to these atmospheric rivers in the future. Are they going to continue increasing like we've seen, especially in the Arctic? We've seen increasing trends. Is that going to keep increasing, or is that more a product of internal variability that will kind of swing back the other way against the background of overall warming? So I think understanding the large scale drivers of these events, especially in the Arctic, is important. I think there's a little more mature research on this in the Antarctic. I think looking at how the decline of sea ice will affect future atmospheric rivers is an important topic that's I don't think has been studied in depth, but I think whether you'll get more of a local moisture source for these events as sea ice declines is important. Yeah, and then ultimately just how atmospheric rivers in these future scenarios will affect how the ice sheets evolve, and ultimately their impacts on sea level rise is kind of the key question that the field is still trying to nail down. So that's all I have, and thanks for your time.
Thanks for that, Kyle. Do you have any questions? Yeah. Jeff has a question.
Hi. Yeah. Yes. The obvious solution to what will happen in the future, of course, is to use climate models, and therefore you can do quite idealized long simulations to get the high end of the extremes. But then the question arises, what resolution of climate model is needed in order to capture these events? Any ideas?
Yeah. That's not something I've specifically worked on. I think in general, for ice sheet surface mass balance, there have been quite a few studies that the resolution matters in terms of the total amount of surface mass balance you get. In terms of simulating an atmospheric river related to the resolution, yeah, I wish I had a better answer. I know the ARTMET project has some studies about using higher resolution models and the implications. So both in historical and future simulations, I believe. So yeah, I would maybe direct you there to look at what the ARTMET project has put out. I can't remember their results off the top of my head about how much it matters, the resolution of the model, but I think there are some answers there.
Yes.
I had a follow-up question to that, which was, there are climate models which have water tracers in them, and therefore you can calculate how much water is being transported and where it's actually originated from. So could this then be compared with the satellite? Is the satellite telling you where the source of the water vapor is?
Yeah, I think that gets tricky. I think a satellite can show you an atmospheric river and make you think that you know where the water vapor is coming from because you can see a continuous, cloud band or, continuous object or whatever. But then if you kind of peek under the hood of what's going on underneath those clouds, uh, it's not necessarily so cut and dry as I think like the water vapor tracer experiments have shown that, in some places along a moisture plume, you're actually not getting any evaporation at all into the moist plume because the moisture gradient is not directed from the ocean to the atmosphere. It's the opposite. Um, so, but then you might be converging moisture from, different latitudes in a more complex way than just looking at the atmospheric river as a unified plume might suggest. So yeah, I think to get at moisture sources, I think a model is necessary at this point, and you kind of have to hope the model does a good enough job to trust its results. But yeah, and then there's also isotope observations that you can make, from the surface that can tell you things about the moisture source too. But again, I think those probably are best used when they're supplemented with models that are tracking the moisture sources.
Yeah, thanks.
Any other questions? 12 o'clock, so I guess we can stop there. There's no more questions. So thanks again, Kyle, and thanks again, everyone, for coming.
Thank you.